Okay, thanks everyone for coming. And if I get kicked out of the Zoom, my slides are on my webpage if you want to have a look at them. So this is joint work with these guys, and that's the plan. That's where I was. So let me begin with some complexity theory. So recall that a language, this may not be the definition of NP that you're used to, but bear with me. A language is in NP if there's a polynomial and a predicate, something that's true or false, that can be evaluated in polynomial time in the size of the input, such that some element is in the language that we're trying to understand, if and only if there exists some witness, something that we can verify of polynomial size in the size of W, such that the predicate is true on both those things. So as I said, it may not be what you're used to. So let's have a look at an example. The set of all graphs which have a Hamilton cycle, it's a language, and it's in NP, you probably know. And the way we would use this definition is to say, well, given an instance of a graph, it's going to be in the language if you can find a linear size path, which you can then verify that it visits every vertex. So that's the definition I want to use for NP, so that I can bump it up to the following definition of sigma KP or PK. So here's the definition. You've got a language over an alphabet, and you're in this strange class sigma KP if there's a bunch of polynomials up to K and a predicate that can be evaluated in polynomial time, so that something is in the language if and only if there exists one verifying thing, then you're allowed to do more. Then you're allowed for all some second thing of polynomial size. Then you're allowed to repeat there exists for all, there exists for all. And then once you've got all these things, you put them all into this predicate, so some sort of algorithm that needs to be checked that runs in polynomial time. And if it's true, then you're happy, you say the words in the language. So this is called for each value of K, we get a different complexity class. And NP is the definition I put on the previous slide of just one verifying thing, whether there exists. And so sigma 2p would be there exists for all, and then sigma 3 and so on. And they all live inside P space. So all of these tasks that we're needing to perform, guessing this finite number of verifying things and then checking for all verifying things, all of this can be done on a Turing machine in polynomial time, polynomial space. Sorry. So you never need more than polynomial space to do all of these things. So they all live inside polynomial space. So that's the complexity class that I'm interested in here today. Okay. So now let me tell you about isomorphism decision problem. So let's see be a class of groups. Consider this problem. On input 2 of these groups, given somehow by some finite description, we need to say yes or no whether G is isomorphic to H. Equivalently, we can express it as a membership problem. The set of all pairs of groups that are isomorphic over this class. And that will be the useful thing to use sigma 2p. So our result, I'll tell you in case everything crashes again, this is the result. That if the class is what's called plane groups, which I'll define on the next slide, then the isomorphism problem, where the inputs are given by a specific finite description, which I will describe a bit later on, the slides have moved around a bit. This isomorphism problem is in sigma 3p. That's our result. So it's better than P space. Maybe it could be improved further. And it's going to depend on this finite description of the groups that I'm going to give you. Okay, so what is a plane group? A group is plane if it's isomorphic to a free product of finitely many factors. The first bunch are finite groups, and then the last bunch of factors are infinite cyclic groups. So we could write it like that, or we could just put a single free group there. That would be the same. An example is PSL2Z. There's a presentation there at the bottom. And so the Cayley graph of this plane group is a big tree made up, well, slightly thickened tree made up of triangles corresponding to the B generator, and these other edges corresponding to the A generator. So that's what a plane group is. And that's the class of groups in which we can decide isomorphism. So, so now let me drill down a bit further into what's going on with isomorphism. So to justify why our result is actually kind of cool, I think. So useful finite description for groups. Well, if they're finite groups, maybe it'd be good to be given the whole multiplication table of the group. But if they're infinite groups, that's not going to work. We need a finite description. So pretty standard thing is to have a presentation. So if they're finitely presented, this would be a finite description. And this is an efficient way to represent a group, like I gave a presentation for that plane group on the previous slide. So we're not going to be looking at finite groups mainly. So the option that we're thinking of is to have finite presentations. However, it's quite famous results that on two finite presentations as input, to decide whether or not they're isomorphic is an undecidable problem. This is Novikov and then also proved by Boone later. So that's undecidable. And then on input a finite presentation, does it present the trivial group? You think, oh, that must be easier. That's also undecidable by Adian and then Rabin. So these problems in general, when the inputs are presentations, are undecidable. Okay, so that's why in the slide where I have my result, I said I need to tell you more than just, I need to describe the groups in some way. So that in general, just given presentations, the problem is undecidable. If we're given two presentations together with a promise that they're in some particular class of groups, maybe hyperbolic group or virtually free group or something. So if we're also given the promise, then it is possible that isomorphism problem is decidable. Okay, you're not going to contradict any of these general undecidable problems if you have this additional information. So let me show you three examples of where this is happening. So Krishtik proved 89 that the isomorphism problem for virtually free groups, so having a free group as a finite index subgroup, is decidable when you're given two group presentations. Seller proved the isomorphism problem for torsion-free hyperbolic groups given by presentations is decidable. And this is the most recent, 2010, Dharmani-Giridel extended the Seller result to all hyperbolic groups, including those with torsion, which is the more difficult situation. So we have decidability for these things where the inputs are two presentations and a promise that they're in a particular class. But what about complexity? So just with the promise, we cannot have any complexity bounds. So I'll try and explain that on this slide. So suppose isomorphism for, let's say, hyperbolic groups was decidable in some crazy space-bound complexity. Or it could be a time-bound or a space-bound. So what could go wrong? Well, if we had this alleged algorithm that ran in this alleged space-bound, then we could input an arbitrary presentation, so not necessarily a hyperbolic group presentation, together with a presentation for the trivial group into this isomorphism problem algorithm. So we can input these two presentations. One of them is, I'm sure you can all come up with a presentation of the trivial group fairly quickly, and then the arbitrary presentation, and then run this crazy 2 to the 2 space algorithm on these presentations. And if this alleged isomorphism problem is supposed to work for hyperbolic groups, the trivial group is hyperbolic. And if the other group is hyperbolic, then the program is guaranteed to give a yes/no answer within the space. If it doesn't return anything within this space, if it's still running and we've used up more than that much space, then, or we've gone through every possible configuration of the space, so we're going to get into an infinite loop if we repeat a configuration. So if we exhaust all the space, then we know that the arbitrary presentation was not hyperbolic. And that immediately tells us it wasn't trivial. So if we had any kind of crazy space bound, we could decide whether an arbitrary presentation was trivial. And Ardian, back in the 50s, I think, has already said that this is an undecidable problem. So I think that that's quite interesting, that we can have decidability for particular classes, but just given presentations, the best we can hope for is decidable. We can't have any complexity bound. So to get a complexity statement for isomorphism, we need more than presentations. So let me give you one example, which is very recent, 2018, due to Senegers and Weiss, that if the input is two virtually free groups, and they're not just given by presentations, we have to do something extra. So the first thing that they do is they give you a context-free grammar that generate the word problem for each group. Now, a well-known result is that a group is virtually free if and only if its word problem is context-free. So this is a reasonable thing. This is a reasonable finite description to give for a virtually free group. And it turns out that Senegers and Weiss proof that if that's the input, then they can decide isomorphism within deterministic space 2 to the 2 to the n squared, which is pretty big. It's a doubly exponential space. They then give a different description, which they call virtually free presentation, which doesn't just mean an abstract presentation, because we know that's not going to give any complexity bound. So they give two virtually free presentations, which I'll define on the next slide briefly. And then they prove that that's in P space. Now, groups that are called plane groups that I'm talking about are a subclass of virtually free groups. And remember that the result that I'm trying to, the title of this talk, is that if we're given two plane groups, they're going to be in a class sigma 3p, which is inside, it's below P space. So our result is, well, it's almonds included. So it's an improvement on these other results that are here. So what is a virtually free presentation? Well, there's quite a lot on this slide, but I wanted to just put it here so you can refer maybe later if you're interested. It's a finite set of generators for the finite index free subgroup. I should say finite index free subgroup, together with a set of coset representatives. So you choose some coset representatives. And then there's some relations which tell you how to move a given word into a normal form where the coset representative is on the right. So we're given these relations to tell you how to put something into normal form. So it's quite a lot of information to be told about a group, a virtually free group. So you're given two of these descriptions, and using all of this data that they have here, they're able to do it in P space, isomorphism. And so there's a few extra conditions, and the final condition here is that the relations for moving the coset representatives past other group elements to the right, together with free reductions, which we always have in a group, form a confluent rewriting system. So I tell you what that is on the next slide, because it's going to lead into to the description that we give for plane groups. So a rewriting system is a pair of alphabet and rules, rewrite rules, left goes to right. And so the rules are just strings over the alphabet. And so the idea is you can replace, anytime you have a factor L, you can replace it by R. So if this was the alphabet and this was the set of rewrite rules, whenever I have a little a next to a big A, I can replace it by the empty word. And so we write the arrow if you can replace this L by the R like that. So in this example, I can replace that by empty. So I'd get A. Then I can replace those two. Then I can replace that. So that's how the rewriting system works. Let's put all this on one slide. The reflexive transitive closure is arrow star. So it's, you're allowed to apply a bunch of rewriting rules to get from here to here. The symmetric transitive reflexive closure is an equivalence between strings, and the operation of concatenation of representatives is well defined on the set of equivalence classes and gives us a monoid. So the elements are equivalence classes with rewriting and concatenation. And so in addition, when the equivalence class of every letter has an inverse, the monoid that we get out of the rewriting system is a group, and we say it's the group presented by the rewriting system. So this example, where the only rules are a big A next to a little a cancels, each equivalence class corresponds to the integer number of little a's minus number of big A's. So this rewriting system actually presents the integers. The second example is if you have a finite group, then you could take every element of the finite group except the identity, and you could have the rewrite rules that say if you've got two elements next to each other, so two letters, you can replace them by this third letter, provided G times H is equal to K in the group. And also, if G is H inverse, then G times H gets replaced by the empty word. So essentially, you take the multiplication table for the group, and that's the rewriting rules. So in this case, the rewriting system that we get just gives us the original finite group back again. So these are my time, I was way too ambitious with my slides. So can I go for a little bit longer and then?
Yeah, I think a minute or two.
On my question. Pardon?
I think a couple of minutes should be fine.
All right, thanks.
We should finish up everything by 25 past the hour, though.
Well, okay. Well, you can just pull the plug on my Zoom again. That's perfectly make me stop. So these are two examples of rewriting systems where the left-hand sides are always longer than the right-hand sides. And so there's some adjectives here. That a rewriting system is finite if the sets are finite, length reducing if it's like the examples we had, terminating if there's no infinite sequences, which of course, if we're reducing length all the time, it's going to terminate. Confluent, a little more complicated. If you've got W reducing to two different things, then the two different things have to reduce to the same thing later on. And that was the word that Senegers and Weiss required their rewriting system to be confluent. Convergent if it's terminating a confluent, and inverse closed if the monoid that you get out of the rewriting system, the inverses are all present in the alphabet. Just a quick picture. So if I have some disjoint alphabets and I have a whole bunch of rewriting systems, then when I union the alphabets together and union the rules together, that presents the free product. And so the corollary is that if G is a finite product, is a free product of finite groups in Z, so that's the definition of a plane group in the beginning, then G admits a presentation by a finite length reducing convergent rewriting system. So my claim is that this is a very natural way to be given a plane group. I can give you a finite convergent length reducing rewriting system. And so the result that I'm not going to have time to go through all the detail is that if the input are two finite convergent length reducing rewritings, which we're promising present plane groups, then we have an algorithm which can decide whether or not they're isomorphic within this complexity class. So that's the main result. So I'll wrap up. So a natural way to input a plane group would be to give one of these rewriting systems. A conjecture, which John Koo is going to talk about a little bit in the next talk, if I stop, is that actually this is an if and only if. G admits a presentation by finite convergent length reducing rewriting system if and only if G is plane. So in that case, it's even more natural to be choosing these because that's exactly, and so this is an open conjecture. It's from 1987, it's still open. So I will not have time to, I'll do one last thing. So this is the key to our algorithm. And it's a result by myself and Adam in a previous paper that we give a characterization of being plane. So G is plane if and only if these two things, if and only if a relation, which I defined and didn't show you, a relation defined on the set of non-trivial finite order elements, if this relation that we define is transitive on just a finite collection of words. So this slide is the key to our result, that we prove that just by checking a finite, quite large, where RT is the maximum length of a right-hand side in the rewriting system. So if we're in that situation, then we check transitivity on all of these elements. And if it is, then the group is plane. If it's not, the group is not plane. And so a whole bunch more steps, and then we end up with the isomorphism problem.
Probably should.
So I'll stop there because I think I'm used up all my time.